I'm going to talk a little bit more about Galileo and Kepler and those guys, because you needed to fill in the exercise that's in the module today. So let's see. So okay. So I guess we need to talk about Kepler's laws. Let me see that. Yeah. So okay. So we just had him getting all excited about putting the Pythagorean solids in between the planets as an explanation of the spacing of the planets. And that was sort of like a mystical experience for him. And then we got to the point where he needed data because it predicted somewhat, the wrong things. Which really was a big part of it was because of lack of data, lack of good data. So he actually then worked with Tycho Brahe. And as I told you, Tycho Brahe had lots of good data. So what that did for Kepler is that it gave him a way to actually plot the motion of the planets through the sky. And he had to try to work out what sort of a shape it was. Of course, he could see to some degree. Would he have plotted? Yeah, probably. But he had to find a mathematical formula for it. So he finally realized, well, it looks like an ellipse, but unfortunately he made a mistake in his 800 pages of mathematics the first time. So he actually he didn't recognize the formula of the ellipse. Anyway, he got it right the second time. So his first law is that the planets orbit the sun in elliptical orbits with the sun at one focus. So this is already a change, right? So he's gone from the idea of circles with the sun in the center to the idea of an ellipse. And an ellipse is a shape that has actually like two focal points. So the sun is one of these. So the sun was in the center if you have a circle, of course. Okay, so there's nothing here. There is another point, which is the other focus, but there's nothing actually there. So this was the first time that somebody had actually shown what is the orbit of a planet. So, and also, remember he'd come up with this idea of the sun sort of flagellating the planet around. So that's also a part of what he did. But he didn't come up with the big difference that Newton came up with, which is the idea of gravitational attraction between bodies. Okay, so this was like his first law. His second law is that the line joining the planet to the sun sweeps out equal areas in equal times. So again, he found this from the data, and he didn't have a computer. So he had to sort of reduce all of his data by hand, and it took him years to do that. So let's see what this actually looks like. So let's say we've got an elliptical orbit, and none of them are this elliptical, by the way. Most of them are very close to circular, but we'll make it like this just to emphasize it. So let's say the planet goes from A to B, in 1 month. Okay, so this is the line joining the sun to the planet. So this line sweeps out this much area in this time. Okay, so now let's say we have the planet over here, and I'll call this A prime, okay? Now what this law says is that the area of the triangle here, the triangle made by the motion of this planet when it's over here, it has to be equal to this area. So if they take the same time, so this is like a triangle pretty much. The area of a triangle is half the base times the height. So because the height here is so much larger, then that means the base here must be larger to compensate. So this triangle must look something like this. So from A prime to B prime, it goes further. It has to go further. Let's say it goes distance big D, whereas from A to B is distance little d. So if the time is the same, then the speed from A prime to B prime is the distance, big D, divided by t. And then the speed from A to B is this distance, little d, divided by t. So from this we can see that d over t obviously must be bigger than little d over t. So the speed is greater when the planet is closer to the sun. So this was what he discovered, and it's pretty amazing, but it's not really quite science yet because he doesn't give an explanation of why this is, right? So he's just sort of found out what happens, but he hasn't shown us why it's happening yet. So in order for it to be science, he'd have to have understood the reasons for it, and that was the next step, which Newton did. Okay, so then the third law is that P is proportional to the square root of A cubed. Okay, what does that mean? Well, if you have an ellipse, this is the major axis. So the semi-major axis is called A. And then the period is the length of time it takes for one orbit to go around. So that says the bigger this A, the longer it takes to go around, which makes sense. But it's not directly proportional, it's proportional with this proportionality. So I won't go into that because we don't need to know that right now. Maybe not ever. But it relates the size of your ellipse with how long it takes to go around the sun. So, okay, so this is sort of changing everything now because this makes it pretty clear. This is only going to work if the sun is at the center here, right? This couldn't work if we didn't have the planets going around the sun, which was Copernicus's insight. So now this is strongly reinforcing Copernicus's idea, the heliocentric idea. And it's probably, well, no, actually, probably this doesn't really freak out the church yet. They may not have really understood quite exactly this. I mean, he hasn't sort of said anything other than just sort of reinforce what Copernicus has already said quite a long time before. But while he is doing this, then Galileo also is busy. And Galileo actually spends most of his time investigating the phenomenon of gravity. So he rolls things down, he rolls balls down inclined planes and times them and puts like, he drops, okay, so let's say you've got two objects, right? You've got this, pretty heavy, and I've got this, which is pretty light. If I drop them and it's like a few hundred feet down, which one is going to reach the ground sooner? So at that time, Aristotle said, well, the bigger one or the heavier one is going to reach the ground sooner. And from Aristotle's perspective, that made sense because the universe was really designed in order for things to be in their natural place. So it was natural for something that's heavier to fall faster. From his perspective, that's what he thought, and that's what everybody thought, because once he said it, it's pretty much accepted. But the difference is that nobody ever thought to try it, right? So they just said how things were. Luckily, Aristotle was really smart, so he got a lot of things right. But he was so smart and he was so right that the things that he got wrong were also just incorporated and actually sort of accepted because it just seemed like he was right in so many things, he must be right in everything. But actually then, so Galileo, the story is that he goes up the Leaning Tower of Pisa and drops them, and turns out that they both touch the ground at the same time. So he discovered that about gravity. But you see, now we're moving into science because he's trying to find an explanation. He's trying to find a reason for things to be the way they are. So Galileo knows a lot about gravity, and Newton is going to use what Galileo has learned, has found out. Like Newton's first law really comes from Galileo. But the place where Galileo really starts causing trouble with the church is because he gets a telescope, right? So the telescope is discovered around this time, and when Galileo gets a telescope, then he can look at Venus, and he sees that sometimes Venus is sort of like this on the sky, but sometimes it's like this on the sky, or sometimes it's like this, right? So he sees that Venus has phases. Maybe there's nothing too wrong with that until you realize the implication is that it's only going to have phases if it's going around the sun, just like the moon going around gives the moon phases from our perspective. So Venus going around would have phases for the same reason, that we're only seeing some part of its illuminated side. So that's a problem because he didn't go to the church authorities to ask about Venus, right? He looked at the sky. He looked directly at nature, and he came out with the truth about nature from nature. So at that time, you just couldn't do that. Everything had to go through the religious authority, or it's just the way they thought. I mean, you just couldn't. Everything sort of had this sort of religious or spiritual connotation behind it. So to actually look for evidence was a problem, right? Evidence challenges the authorities. So we're looking at this, the faith on one side, gradually turning over to the reason on the other side, human reason. This is a problem for the church. Actually, not a problem for humanity, but a problem for the church at this point. So here's Venus. Then he looks at Jupiter. And so night after night, he looks at Jupiter, and he sees that it has 4 moons orbiting around it. And you can see like a whole series of drawings. And one thing you notice right away when you look at those drawings is that it changes from night to night or week to week. right? So, in other words, the heavens are supposed to be the unchanging realm, whereas the earth is the realm of change and decay. So now you're really starting to challenge orthodox thinking. But of course, he actually saw it. So people who were willing to use reason accepted it. You know, you can't really deny what you can see directly. And that's a big problem for the church. And then on top of this insult, he goes to the moon. When he looks at the moon with his telescope, and you can do this with even a small telescope, he sees that there are mountains, there are craters. It seems to be a world very like the Earth. So, so Galileo gets into trouble. He doesn't get killed like Giordano Bruno did, just I think a little bit before Galileo, probably. But he gets put under house arrest, and he's forced to renounce his ideas. Let's see, is there anything else I need to say? I think this is good. So anyway, this is like, you know, the scientific revolution. Just the beginning of it. So it's really all about challenging authority. What is the source of authority? And eventually, of course, the Catholic Church realizes they were wrong, and Galileo is forgiven. When was that? I forget, actually, but it was like about 30 years ago, maybe. Recent. So he was considered, you know, a heretic for all those years, like 300 years, more than 300 years. On the day that Galileo dies, or at least in the year that he dies, I don't know if it was the same day, Newton is born. And then Newton sort of brings all this stuff together under Newton's laws, which I'll talk about on Monday. Newton's laws they incorporate all of Galileo's discoveries about gravity. They incorporate and explain Kepler's laws using the force of gravity. So, but they do turn the universe into a machine, which is a bit of a problem, although it was a problem at the time, and then it was forgotten for like 200 or 300 years. People didn't really worry about it, apart from a few philosophers. But now actually people are thinking about it again, because it's clearly not a machine when you look at quantum physics. Okay, so I'll stop here, and then we'll resume this on Monday.